Okay, so good morning everybody, and today we have the pleasure to have Kareljan Schoutens from Amsterdam, who will start his lecture about many-body physics and quantum computation. Please.
Well, thank you. So I'm very happy to be here in Florence, despite circumstances, and too bad many of you are connecting from a distance. But I hope you can still, be part of this lecture series and, learn a few things from it. I have a lot of time with you, I think like 10 hours, so I'll try to build up a story from the beginning and take you along with that. So I think there is some way I can take questions, and so please speak up if you need explanation. Also, after the lecture, via email or so, you can always connect me for explanations. So my story is, it's about two things. Let's put some. I'll be talking about quantum many-body physics. So I'll use this abbreviation to speak about that, and then I'll be talking about quantum computing, or quantum information, quantum information processing, these kind of things. Now I think quantum many-body physics is probably your bread and butter for many of the participants in this school. But just to be sure, so this is analyzing systems use, quantum degrees of freedom. So this could be spins, this could be fermions, electrons. You could be talking chemistry, trying to understand a molecular structure, could be a spin chain, could be a Hubbard model for correlated electrons. This is the setting for that. Typically, these degrees of freedom of interactions, typically these are strong. So we talk about strongly interacting, strongly correlated states. And we all know that this combination, if you have a few degrees of freedom, and they're quantum and they're strongly interacting, then it's a difficult thing to analyze, right? So quantum degrees of freedom come with Hilbert spaces. Hilbert spaces have big dimensions, and typically what you're looking at are operators in these dimensions, and it's a big headache sometimes to get physical answers out of the formalism for quantum many-body theory. So typically, what you're after to know correlations, functions. You would like to know dynamics. So you start your system at time 0, you let it go, and you try to predict what happens quite a bit later. And obviously, in the end, the big goal is to connect to experimental observations to explain what happens in materials, etc. So that's topic number 1. Then there's topic number 2, quantum computing, quantum computation. Yeah, you probably heard about that. So this is the idea that this is computer science, but computer science where let's say the carrier of the information is not a classical computer with zeros and ones, but it's a quantum computer where the degrees of freedom 0 and 1 are replaced by quantum degrees of freedom. It's kind of notation, so we bracket for the 0 and the 1 state, and this is what we typically call a become qubits, and the information for our computer science is carried by a quantum system. So then, qubits can be made to evolve stepwise. So there's typically you do a stepwise evolution of the state of a qubit or a bunch of qubits. So that under the name of quantum gates. And what these things do, they build up a thing called a quantum circuit, and then in the end, you typically do measurements to read out your system. So maybe let me make the standard picture. So a standard representation of this kind of qubit quantum computing setup, which is drawing lines representing qubits. So suppose my computer has 3 qubits sitting there. I draw them from left to right. So there's some initial state. Let's imagine I put 3 qubits in state number 0. So that's the quantum register, so to say. Quantum register, typically a collection of qubits or a variation. Some people like to work with qubits, where there's more than 2 states. So that's you start a quantum computation. Then there's this stepwise evolution that I mentioned. So that's applying quantum gates. For example, I do something to a qubit. I flip it, so I use an AND gate, a NOT on that second qubit. I can do something to, let's say, 2 qubits together, make a CNOT combination. I'll come to that later, what that is. I can do a few other things. At some point, I'm happy with my computation. I stop it, and I do a measurement. So I measure what is the state of qubit number 1. So I have some kind of measurement device here on all my qubits. And out comes a bit string, a classical bit string. For example, it could be the output is, for example, 001. And then, the art of the quantum computing business is to build quantum circuits and run them in such a way that what comes out of here, so this is the quantum output, so to say. So that what comes out of the computation is an interesting piece of information, right? So you like to program this machine such that it computes something for you, which is interesting, and in the end, you would want that to be actually something you couldn't compute using a regular computer. That would be the big dream of this whole field. Okay, so this is a very sketchy representation of quantum many-body physics and quantum computation. And now, in a sense, the theme of my lectures, which will be coming back, is this arrow. There's this double arrow here, indicating some kind of relations. And so let me consider the direction here. So what can quantum many-body do for quantum computation, so to say? Well, this is a physical machine. So I'm drawing a diagram here, making it very abstract. But in the end, these qubits are physical 2-level quantum systems. So yeah, I was getting to this connecting quantum many-body physics, quantum computing. And what I was bringing up, the quantum computing scheme that I put here as an abstract flow diagram is actually a physical machine, right? So these qubits are 2-level quantum systems. They can be atoms, they can be superconducting islands, they can be trapped ions, all kinds of things. And the operations that I put in the middle are quantum control things. So you try to rotate a qubit from state A to state B, or you try to make 2 qubits interact in a very delicate way such that they do a certain operation on the 2 of them. But this is clearly highly subtle and non-trivial physics, and all kinds of insights we have about many-body physics, for example, 2-body interactions that could implement a 2-body gate here. They can be used and they can be exploited to improve, let's say, your quantum computer design. So there's this quantum control notion. For, in particular, quantum gate design. And I'll bring quite a bit of that up in my lectures. I'll show many examples where I explain how we do these things in practice. You can try to push this a bit further. So one theme that I'll bring up in this lecture, which is a bit unusual in the field, is to imagine having not 2 qubits talk to each other, which is the standard thing to do, but try to exploit, connecting more than 2 qubits at the same time. So imagine some really many-body interaction with more than 2 qubits involved that we can control well enough and try to exploit that to make a quantum gate. So you can try to improve schemes depending on what hardware you have in mind. Improve, let's say, things using multi-qubit directions. And again, if you go in that direction, you need more and more sophistication in controlling many-body interactions and see what they do for you. Now, the third arrow is actually in the other direction, which is why this field is so interesting, I think. So imagine somebody builds a quantum computer for you. You're not involved, but you get the results and you can play with it. So that's a tool, right? So that's a computational tool that's different from your laptop and your supercomputer, and that's quantum on the inside. And it's quite natural to expect that a quantum computer can do wonders for you in analyzing hard questions in quantum many-body physics. I think this is the original motivation of Feynman back in the 80s. He kind of anticipated this. He said, let's build a quantum machine to do quantum computations to analyze our quantum physics. So that's the other direction. So now use a quantum computer, imagining it's all up and running as a tool for doing quantum many-body physics. And let me add here chemistry. So one of the expected applications of quantum computing, that's probably one of the ones that's easiest to arrive at and be serious about is quantum chemistry. So you can imagine analyzing small molecules with maybe 3, 4, 5 atoms using a quantum computer. And these things happen as we speak. It's still on a small scale, but there's lots of progress. And if you imagine having, for example, a quantum computer with, let's say, 100 really good qubits that don't make mistakes and that you can control very well, then you can probably outperform classical hardware for doing quantum chemistry. And probably 100 qubits could be enough to do that. So that's spectacular expectations. And again, as a physicist like myself in this field, there's lots of things to do because there's this arrow from left to right where you can try to contribute to, let's say, hardware design using your physics insights. And there's the arrow in the other direction where you use the quantum computer as it comes to you to do your physics and chemistry analysis.
Kareljan,
yes?
with respect to the last point, namely quantum computer in helping understanding us physics, don't you think we'll go in an analog computer, not really binary?
Yes, very good question. So for the people at home, the question is that there's analog and, let's say, binary or digital computing. And it could be that the analog version is the actual thing that helps us along. I prepared some remarks about that. So there's an extra thing which I would like to call quantum simulation, which is, I think, very close to analog quantum computing, so to say. And that's yet another notion which is slightly away from what I brought up so far. So let me say what that is. And there's some confusion about what we mean by this, so let me talk about that. So I think that the most direct interpretation of quantum simulation is that you're interested in your quantum many-body system. Let's say number A. Let's say that spins in some material, and you like to understand their correlations. You can't quite you can't get your measurements well enough, or you can't do your computations well enough. So you can imagine building, let's say, engineer a sort of a lookalike quantum system, quantum many-body system B, that you can control much better in the lab and that you can do computations of. So for example, you analyze correlated electrons, you think maybe a Hubbard model would be a good thing to try. It's very hard to analyze, so you could try to build, let's say, a Hubbard model situation using cold atoms rather than electrons and do measurements on that and learn a few things. So that, I would say, is a narrow notion of quantum simulation. So you build it and you do measurements to learn things and measure. You could also say, a slight variation of this is from the point of view of theory. So suppose there is some model Hamiltonian, that's again 2D Hubbard, which is very difficult. We don't quite know what it does. You can imagine, simulating that. So if a theoretical let's say, problem or system in quantum many-body, you can try to address it again by doing a simulation, so building, use an actual laboratory system to analyze. And again, these will typically be not like this here, but they will typically systems with interactions on between many parts of the system. Right? So these things are possible, and now obviously there's a bit of a gray zone between simulation and computation. So you can try to say there's digital quantum computing, there's analog quantum simulation, but some schemes that we use, like VQEs and others, are a bit in between. But there's these two sides of things, and both of them are interesting and also happening as we speak. There's many interesting examples of this situation that are materializing today. Now, one more thing, I guess to get my glossary right, there's yet another notion of quantum simulation which people use, which is that, suppose you're interested in this kind of thing, a quantum computer is, let's say, 20 qubits doing a certain computation. We don't have a good quantum computer with 20 qubits doing this computation, but, you can use your laptop to mimic that situation. So you can program a classical computer to behave as a bunch of qubits and to do quantum computations. And sometimes people call that quantum simulation, but there's the confusion, because that's a different thing from this here. So let me maybe say that we rather call quantum emulation. So that's a different word, let's keep it for that. So that is, how do we say this properly? Yeah, so let me keep the word, so you're emulating a, let's say, quantum circuit on classical hardware. So actually, I'll show some of that in my lectures. I used one of these platforms. I did a bit of coding, and I'll show you how that goes. And in that situation, I used my laptop to emulate, so to say, a bunch of qubits, maybe 5 or 10. That's easy enough for a classical computer. So this is not the real thing. It's
Kareljan, sorry, someone is asking you to write a little bit more clearly on the blackboard.
okay. I'll try to do that. Yeah. So again, this emulation thing is not the real thing. So it's really, learning about how qubit systems behave by emulating them on a classical computer. Clearly, you can only do this if the number is not too high. Let's say you can do 10 or 20 qubits, and that already takes 2 to the 20 dimensions of Hilbert space. On a big supercomputer, I guess you can go to about 40 or so, but that's where it stops. So, up to that range, we can learn to work with quantum computing circuits by emulating them and see how they behave, and we can be fancy, we can add a bit of noise, and we can try to be as realistic as we can. But in the end, it's like a warm-up exercise to learn how to work with the real quantum hardware, because as soon as the number of qubits goes over, let's say 50 or so, you can forget about this emulation, and it's impossible, right? But it's an important tool as we speak today. So all these things that you hear about, many, if you, for example, try to use one of the, let's say, cloud platforms for quantum computing, and you put in your circuit using some language, you typically get two options, right? One is to emulate, and then the platform calls the supercomputer to emulate your quantum circuit, or the option is to actually run it on hardware, which is a different thing. Typically, the results that come out are much better for the first than for the second today, because the actual hardware is far from perfect. So it's a useful thing to have the two available. But in the end, the emulation will stop. But this will be, a number of qubits. Well, up to something like 40 or 50, and then you can no longer do this emulation on a regular computer. So yeah, this was like sort of my introduction, setting a bit the scene and also the terminology that I'll be using. So I'll now zoom into some of the details. Let me make room on the blackboard, and I'll promise to start writing a bit bigger. So yeah.
Before that we go on, just to elaborate a bit on the question of Giuseppe. So, you gave the definition of qubits, the quantum computer in terms of qubits, and I understand that there is the idea that we want to do with quantum system, we want to do the same thing that we were doing with classical computer with quantum. But do we have a strong, so final evidence that that is the best way to do quantum computation? Perhaps some analogic version of it, or hybrid, or something else that we didn't figure out yet, let's say.
No, fully agree. So I think so the narrow context of these quantum circuits is very nicely defined, and within that context you can for example try to determine if certain things can be can go faster on quantum computer, yes or no. But as a physicist, indeed, we know about all these other things, and we can imagine all kinds of ways where we control a quantum many-body system, and we make it look like a Hilbert model, or we make it look like something else, and there may be completely unexpected directions still open. For example, running quantum dynamics for a long time, can give all kinds of new things, like we discovered quantum many-body cars doing these experiments, and yeah, that's in a sense a quantum computing discovery, but of a different type than programming circuits. Yeah. So, but let me certainly for today give you some of the, let's say, classic pieces of how quantum computing is done. So let me call this little chapter of my lectures Quantum Computing 101. So yeah, depending on where you come from and your background, you may have seen this. I think many of you have seen some of this, but let me simply get into the story, and hopefully you'll learn a few things on the way. So yeah, what do we need? We need a two-level quantum system. Let's think qubits and not trits and bits, etc. So those two states. So typically, as a physicist, you say typically, there's a spectrum. Two states stand out. There's, let's say, a ground state, and then there's some first excited state. And let's imagine that we can somehow, restrict everything to these two states, and that's our qubit. Okay. So typically the two states we call in quantum computing language 0 and 1, as I mentioned. But they could be two atomic levels of strontium, so and so, etc. And then we can talk about these 1 qubit states. And there's a standard notation for doing that, which is called Bloch sphere. So we call two angles, theta and phi. And we define a 1 qubit state by saying we take cosine theta times the 0 state plus sine theta e to the I phi times the 1 state. So I use two real parameters, two angles, to give a 1 qubit state. Now you may say that's not enough because I can put two complex numbers in front of 0 and 1, so that's 4 real directions. But then there's two things. First of all, you want the thing to be normalized to unit length. That eliminates one real direction. And then there's an overall phase that you don't care about, which eliminates the second overall number. So you can do with two numbers, and with theta and phi you completely nail the 1 qubit state. This is typically called Bloch sphere, so you can make nice pictures. Representing the qubit state using these two angles. So that typically goes like this. Maybe let me make it bigger. at home. So the block sphere would look like this here. There's the north pole, that's theta equals 0, that's the state 0. There's the south pole, which is theta equals pi, and that's the state 1. And then there's states in the middle. For example, a typical state, which we often see, is this state 0 plus 1 over root 2, which is often called, noted like this. So that sits somewhere on the equator, right? And then on the other side, there would be the state, let's say 0 minus 1 over root 2, which is the state called minus. That sits on the other side, and there's states with eigenstates of the y operator, etc., etc. And it really helps. Yeah. Sorry. Yes. Very good. That's over here, right? Because I will give me. Yep, like this. Thanks. Funny representation, but it's really helpful if, for example, if you're figuring how your one-qubit gate should be chosen, how they compose one after the other. You imagine this block sphere and you see your one-qubit state like a big arrow pointing on a sphere, and one-qubit rotations are rotating your one-qubit arrow in all these directions. Yeah. Okay, so that's the one-qubit situation. I think this is about all there is to say about that. Imagining a bunch of these qubits, so typically, let's imagine the number is n, so we have n qubits now, meaning we open up 2 to the power n dimensions. And now we can imagine acting on this, so do some kind of physical processing, put a magnetic field, send a laser beam, and what that typically does, so the most general operation would be some kind of unitary operation. The n by 2 to the n, so to say. That's the most general quantum operation. And so, whatever computation you would like to implement using these qubits, should be happening via a well-chosen unitary. So, in a sense, if you want to be general and universal, you like to be able to implement any unitary of this huge size to the n by 2 to the n. So that sounds like a big challenge because, in a sense, your gate collection should be extremely rich. You want to have all these unitaries to build circuits. But now there is this good news that there is a result called universality, which is that you can build unitaries using only a few building blocks. So there's a theorem, if you wish, called universality. And that states that you can build any U by iterating 2 ingredients.
We see the problem with the sound. Keep going.
Okay, so universality means that you can build unitaries by combining 2 things. One are qubit rotations, and the other is a particular this is the statement. If you have control, say, of 2 kinds. One is that every individual qubit can be rotated on its block sphere in whatever way you like. So that's a U2, unitary with only 2 dimensions. And suppose there's also an extra thing you can do, which is this 2-qubit CNOT gate. Then you can build everything. So now what is CNOT? CNOT is the following. Suppose you have 2 qubits. So they can be in CNOT does, it's written like this. CNOT does a NOT, so an X if you wish, on qubit number 1, but only if qubit number 2, this indicates provided condition that number 2, qubit 2, is in state 1. Okay, so the table for a CNOT gate is the following. If qubit 2 is in the 0 state, nothing happens. So these two states are inert. Sorry, not these two, but these two. But then, if qubit 2 is in the 1 state, it flips the first one. So that happens here. So this one flips to 1.
Kareljan, sorry, it's better if you stop a bit because they cannot hear anything. So.
Let's try again with this. Okay, is it okay?
Yes.
Then not put in the. Let's put it here. Or here. Maybe it works better.
Sure.
You speak.
Yep, I speak.
Is it working? Speak.
Yep, speak.
Seems better.
Seems better.
For the time being. And then also the writing is starts some problem.
But the chalk is not good. Should
Chalk is
buy
not
another
good. Try
chalk.
this other chalk.
Okay.
And,
So everything's fine except the talking and the writing.
everything is right about what? The weather? I don't know. Keep going.
Okay, so I was completing my truth table of the CNOT gate, and I was telling you it flips the first qubit conditioned by the second qubit being in the 1 state, right? So if the second is 1, then this goes to 0. So this is a unitary operation, you can check that. It's non-trivial, it entangles the 2 qubits. So if they were independent before, after going through a CNOT, they form an entangled state. Maybe one more thing for notation to be sure. So this is a bit long. I can also say, if I start as A for 1 and B for 2, where A or B are at 0, 1, then what CNOT does is pretty simple. It keeps the B the same, but it flips the first one to A plus B mod 2. So if B is 1, it goes from 0 to 1 and from 1 to 0 on the first qubit. Okay, so that's what CNOT does. And now the theorem, once again, is that any U on n qubits can be built by piling up lots of 1 qubit rotations plus CNOT rotations. So let me give you one example for that. Let me go here. So suppose, I do 2 qubits, and my favorite gate that I like to realize is the swap. Okay, so I like to build the swap gate, which simply sends whatever I put in A and B, so in 1 and 2, it sends that to the other combination, B. So this is, this is not CNOT, this is a different gate. So now the theorem tells me that somehow I can realize a swap gate by combining CNOT and 1 qubit rotations. Right? I can somehow build a circuit involving a bunch of CNOTs and things to make this swap. So let's see how that goes. Anybody has a idea how this goes? I don't think it's easy for me to learn from the people there, but okay, so let me then give this to you. So actually, it turns out you need 3 CNOTs to do this, and the funny thing is you build a combination. So you do a CNOT like this, you do a second one in the other direction, and then you do it again. So theorem, this circuit actually performs the swap operation by combining 3 CNOTs. You don't need one-body gates for this case, but you do things. Well, let's do one check. Check. So let's take one from my table, for example, 1, 2. So 1 for qubit 1, 0 for qubit 2. That's the ingoing state. So that means, I start with 1 here and 0 here. So let's make the 3 steps that my circuit is telling me. First step, I do a conditional flip of the second given the 1. And since the 1 is in the 1 state, something happens there. So after the first step, I have a change from going to this, 1, 2. Then comes the next step, I do the other CNOT direction, and again something happens. You can follow, so now I'm going to flipping the first one, 0, 1, keeping the second one as it is. And then comes the third step where I condition on the top qubit, but that's 0 now, so nothing happens anymore, and I'm done. So final result, 1, 0 has swapped to 0, 1, as it should be in the swap gate. Right? So you can check all 4 states, and it works, and this proves that this circuit here correctly builds up the swap operation. So that was a very simple one, but again, the theorem tells me that whatever you like to do with n qubits, quantum Fourier transform, some crazy rotation, you can do it by piling up lots of CNOTs and 1 qubit gates. And that's extremely useful, because it means that, on the experimental side, if the builder, so to say, can, realize a CNOT operation, and they can do 1 qubit rotations, then it's good enough. Because then everything can be done. Oh yeah, so CNOT is available on most, let's say, qubit platforms. I think the first successes were late 90s. For example, for 2 superconducting qubits, they achieved that, but now it's quite standard that they can do this. I'm coming to that. So my next sections are about examples on how this is done in practice, so to say. But it can be done, and I think many machines today, they do this with fidelity, or they do this with fidelity, 0.999 or so. So they're really good at this, and you need this because a typical circuit has lots of CNOTs, and the fidelity is crucial. If there's a too big mistake, then it piles up and it destroys everything. Okay, but yep. So let me keep going a bit, or is it already time for a break? Okay. So this, again, this was the general, I guess, QC 101. Now let's actually make this more concrete and, imagine that our abstract 2-level quantum system is actually a spin-a-half system. A thing we know very well. And let's, imagine certain Hamiltonians for that and see how we can use those to control our qubits. That's much better, Andrea. Yeah, so next chapter, spin-a-half. Okay, so very simple, spin-a-half, we typically write, the SZ equals plus bar over 2 like this. Now let's today, switch to that, or identify this. So the quantum computer scientist will say 0, 1, and the physicist will say up and down, right? That we can easily translate. Now let's imagine first, let's do a single qubit, and talk about many of them a bit later. And let's imagine, let's talk about these 1 qubit rotations, how we can do that. So, now let's do physics. So so the goal is, understand the 1 qubit rotations. Now, so I guess in physics, the only thing we have is, put some Hamiltonian, put some interaction, and make it work for you. Let time run and change the state. So what we can have, imagine using a magnetic field. That's the obvious thing to do here. And so let me, for example, be extremely simple. Let's put a B field in the x direction, meaning that we're going to have some kind of energy, some Hamiltonian, which is a constant times Bx times Sx. So this is the B dot S interaction of a field with a spin. And Sx, of course, is 1/2 times the power of the X matrix, which I would call X in the computer science language. So this would be 1/2 times G times Bx times X. Where X, Y, Z, just to be sure, I use this notation. X is this matrix. Y is this matrix. And Z is this matrix. So this is the Pauli X, Y, Z. So this is the interaction that nature gives you. Magnetic field comes close to a quantum spin. So this means if you now pulse, so if you put a Bx field during a time t, so put a pulse with time t, so that generates a unitary operation on the qubit, given by the Schrödinger equation. So that gives us a u, which is e to the minus I times t times the Hamiltonian. Since Hamiltonian is time independent, this is easy. So that's e to the minus I times t times g bx over 2 times my x matrix. So this is the little exercise of exponentiating a Pauli matrix, which you can do in various ways, but I think you've seen this before. It gives you the following result. There's a cosine of the time factor, which is, g bx t over 2 times the identity, and then it gives minus I times the sine of the time factor, g bx t over 2, and then the X matrix itself. So one way to actually get this result, you can use x squared equals unity, which is the same, happens for all these three matrices. So if you then build a Taylor series for this exponent of a matrix, all the, let's say, the even terms are identities and they build up the cosine, and the odd terms are x's and they build up the sine. And you get this here. But now you see that how you can actually, so you can choose the t you like. So you pulse, let's say, bx during time t, and that gives you this unitary. And there's particular choices that you can make. For example, if you pick, gt bx over 2 to be, what is it, pi over 2, then time goes and the whole unitary that you built is minus I times. Now the minus I is not important, it's an overall phase, and so you've in essence realized the X operation in a physical way. Right? And so you can do the same thing. You can, for example, this I could call this Ux. You could pulse the Y or the Z directions, that would give you these matrices and the same kind of result. And if you actually combine these things, you can build whatever one qubit rotation you like. So this is rather simple. If your hardware is spin qubits, as some people actually build these things, then the 1 qubit rotations are magnetic field pulses that you have to control very precisely. I was planning to provide some exercises. I'll put them on paper by tomorrow or so, but here would be the first one. Suppose you have available, so exercise, this is maybe not a good color. So I have a 1 qubit exercise, a 2 qubit exercise, and a multi-qubit exercise. So this is the 1 qubit exercise. Suppose you have available, for example, Ux, so the one I just built, with general time t, and also UZ for some time t. How do you make all the rest? For example, suppose you want a famous 1-qubit gate, which is called the Hadamard gate, typically written like this. That's this matrix. It's an important gate. It's the gate that completely mixes the 0 and the 1 state in a superposition. So you want to make that, but the only tools you have are UXs and UZs. How do you do that? Can you combine UX, UZ in a certain way to build a Hadamard gate? So build. And I guess one clue is that you'll need 3 of them to do it. 1 or 2 is not enough. But you can do it. And again, working these exercises, it's really nice to have this block sphere, on a piece of paper, and then you really can visualize all these things. For example, this UX, I guess it's a rotation. The UZ would be a rotation, along the equator of the block sphere. UX would be a rotation along a meridian, etc. So that's nice to visualize how that goes, and it's relatively simple. And each qubit type comes with its own control, I guess, to do 1-qubit rotation. So for example, if you're talking atoms and ions, you typically use laser pulses to do these things. But if it's spins, you use magnetic field pulses, and that's, I guess, the easiest to visualize. Okay, so I guess that was easy. Now let's talk about the 2-qubit gate situation. And for that we need interactions. So we need to specify how 2 qubits can talk to each other. So let's talk about that. So that's, let's say, spin interactions. And I guess, employing them to make quantum gates. And here, I guess you have to work with what nature gives you, right? So if you put 2 spins next to each other.
Maybe we can take a break now. As you wish.
Yeah, that may be good. So maybe this is a good moment to put a little and let's do this for after the break. Very good, thanks.
We come back in 10 minutes. Well, actually at 11, 7 minutes.
Okay. So welcome back. So before the break, there was some general discussion of quantum many-body quantum computing. I gave this quantum computing 101, so the abstract setting with qubits, circuits, measurements, etc. And now we're zooming in on physical systems that can do these tasks. So we decided to look at spin 1/2 as the information carrier. So once again, if you're used to spin up, spin down states, I'm today calling them 0 and 1. And if you're used to sigma x, etc., I'm today calling them x. But it's all the same things that you've seen before. So we discussed that 1-qubit rotations can be magnetic, and if you have enough directions and pulse times, you can build whatever you like. And now it's time to talk about spin-spin interactions. And there, you have to work with what you get from nature, right? So if you bring spins close to each other in certain settings, they will interact with each other. And the Hamiltonian that does that, depends on situations. So typically, we can have the following. We can have what's typically called XX. So let's say the Hamiltonian for 2 qubits interacting would be J times the X operator on 1 times X on 2. Or you can also think it's Z on 1, Z on 2. And that's what you call Ising, right? This is the Ising interaction. And many systems have, for example, trapped ions, which is to do quantum information. They typically have as what's called native interaction, an Ising interaction. You can have what I guess many people call XY, where the H would be, again, some strength, and then X1, X2, plus Y1, Y2. So this is, well, I guess many physicists call the XY model. This happens, many systems have this. For example, superconducting qubits typically talk to each other with this type of interaction. And then there is what we are well used to in physics, let's say the XXX type interaction, Heisenberg interaction, where the H12 would be some J times X1, X2, Y1, Y2, Z1, Z2. And this is the same, as it's 4 times J times S1 dot S2. So if you write the spin operators as a vector, as we're used to in physics, and then the S dot S, the SU2 invariant spin-spin coupling, if you write it out, the spin, so the S operators are like half times the Pauli matrices. So if you work this out, it looks like this. Yeah, I guess this is a bit tricky, depending on. So you like this to call this XX? Yeah. and I don't call this then. Okay. So then I guess this deserves to be called Heisenberg, right? And the special thing about the bottom choice is that there's an SU2 symmetry, which is respected by this coupling, right? As you see from this S dot S notation. So all these things are possible and they'll happen. So if your hardware has actual spin halves, which is again a design that's being built and explored, then this coupling is the natural one that will happen to you. So like my colleagues in Delft, they isolate spins on little quantum dots, and they have a way to actually kind of squeeze them close to each other during some time, and while they're close, they have this S dot S interaction running, and then if you've had enough of that, you again separate them and they stop interacting. And this way you can pulse an interaction like this one over here. So that's, I guess, the idea that somehow experimentally, we have control of pulsing these interactions between 2 qubits of our choice, typically nearest neighbor qubits in the hardware. And now let's imagine we can do that. And now let's go to our task, which is build a CNOT. Because I gave you this theorem that if we can build a CNOT and the 1 qubit rotations, which we already checked, then we can do everything, right? So if we can build CNOT using this physics interactions, then we are in it. So the big goal, build CNOT. Well, CNOT is enough. You can work around it. You can imagine you have another 2 qubit interaction and try to see if that's enough to make everything. And that's in sense what we'll be doing, right? So the native interactions that we get from there are not CNOTs, but I'll show you can actually make a CNOT out of them, and from there you can make everything. And yeah, you can. So there's I swap this and that, and there's alternatives that are probably as good as that. So there's all kind of variations on the theorem. And there's also variations where you only use certain 1 qubit rotations, not all of them. But the message is that in general you can do it. But let's stick to the narrow scheme and try to build a CNOT from what we have here. So let's first take the in case. And maybe I think it's a bit more convenient to use the Z basis. So let me imagine, we have the Z1, Z2 interaction available. So let me try to demonstrate to you how, if we have this, how we can actually make our CNOT gate. So now let's build exercise. So I'm working in a 4-dimensional space, right? With basis of the 2 qubit states. The standard choice is, you do 0, 0, 0, 1, 1, 0, 1, 1. So on that basis, I can write 4x4 matrices for my operators. So let's take the following, which I like. So I do this Z1, Z2, and I add a bit of Z1 and a bit of Z2. So the 1-qubit things. So let's imagine we can make this thing here. Now, as a matrix, you can write this out. It looks like this. It's -1, -1, -1, plus 3. For example, you know, the one down here, that's 1, 1, which means the z is equal to -1. So that means all 3 terms are +1, and I get the +3, and the others you can figure, you get this here. So what this is, you know, -1 times the unit matrix, -1 times, you know, the unit matrix, and then +4 times this matrix here. Okay, so that's a thing I can imagine having in my lab and working for me. So if I that thing, I can make an exponent, and if I take a smart choice, so I pulse this for a certain time, giving me e to the pi I over 4 times this matrix, Z1, Z2, Z1, Z2. So this I can make, that's, let's say, my U. And if you see how that goes, so the -1 identity gives a phase. Let me write it to be complete. So that's e to the minus pi I over 4. And then the second thing, so I put pi over 4, there's a 4 there, so I get e to the pi I, that's a -1, but only one location, so I get 1, 1, 1, -1 as my matrix. Okay. So this is the unitary that I can generate by pulsing this combination. Okay. Yeah, and now let me continue a bit on this side here. What I have now, so forget about this phase. I have, you know, an operation that sends, well, let me go slow. So it sends 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 0, and 1, 1 to minus 1, 1. I picked up this minus. It looks like a minor result, but it's all we need. So in circuit notation, I would call this like this. So I guess let's do it like this. So this is a control Z. Okay, so you can see if I control on the first qubit, and if it's in the one state, I do a Z operation. So I put a minus to the other one. So this is what I made. And now you said, well, my goal was to make control X, right? I was going to make this, which is the same as this. So we're not completely there because we're supposed to make this. We made this. You know, there's a little matrix identity, which, you know, if you remember, this is one of my 1-qubit rotations. So you can check, you know, that's easy, that h times z times h equals x, and also h times x times h equals z. So that's, you know, it's change of basis in a sense. And now you see that it's all done, because I can go from z, which I have, x, which I need, by putting a bunch of h's. So you see, if I now do this, make a circuit where first I put an h on my second qubit, a Hadamard gate, and that's a 1-qubit rotation, that was done. Then I put my new device, which is the control Z, which I can make using physics, and then I put another h on the second qubit, and this is the same thing as the CNOT. End of proof, right? So you see, it's really nice. I use this interaction that you know, nature gives me in certain systems. I make a nice combination. I pulse it with just the right amount of time, so it gives me this. And then I do a little, you know, upgrading using 1-qubit rotations, and there's my CNOT. So this is how this system can do the trick. So that's really nice. Second system, let's do all of them, because they're all important. You know, they are all happening in practice. I'll skip the second one. I'll go to the third one and try to do the same analysis. It's a bit more difficult, I warn you, but it can be done. So yeah, let me erase this and make room for my next example, which is the XXX case. So now what we have is this XXX interaction, and we can pulse that. So yeah, so this is my third situation for building CNOT. It's Heisenberg. So now what I have as a native thing is pulsing the XXX interaction, the S dot S interaction. And again, physically, it's done by pushing the spins a bit closer, having them there for a while, and then putting them away again. So this means that what I have as a native gate, as it's called, native gate, is essentially the exponent of my interaction. Now, following some conventions that I'll use later, I'll call this thing Heis alpha. This is a notation I picked from one of our graduate students. And let me define it like this. So I put some phase for convenience, e to the minus I alpha over 4. And then I put e to the minus I alpha. And then let me write it. So this is, what is available in my system, because I can turn on the S.S interaction, have it there for some time, which sets an alpha, and then turn it off, and that gives me this unitary operation. So Heis alpha is a unitary, on dimension 4 that I have available. And so the question is, if I have Heis alpha, how do I get my CNOT? Now, to be explicit, let me actually give this whole thing again as a 4x4 matrix, so you know what we're talking about. I hope it fits over there. So there's an e to the minus I alpha over 2 in the corners, also down here. And then there's lots of zeros here. And there's a 2x2 thing in the middle, which is actually cosine alpha over 2. And then it's minus I sine alpha over 2, minus I sine alpha over 2, and cos alpha over 2. So this is the matrix. This is a unitary operation that's given to me by the physics of, SU2 spins. And again, the challenge is to build a CNOT out of this constituent, so to say. Now, so how do we do this? Let's look at this alpha. So note, if I do this thing and I put pi for my angle alpha, so let's see what that gives. And then the top thing there becomes minus I, right? Yep. I minus I down here. And then the cosine vanishes, and I'm left with minus I off diagonal. So I have this thing here, minus I, 0. This is seen before in my little exercise that I gave you before the break. So it turns out, what the Heis interaction does, if you let it run over time, it ends up doing a swap on the two spins. And I think many of you know this, right? If you do beta ansatz for XXX, you use this kind of things. It's a permutation operator. So that's nice. I told you before the break how you can use 3 CNOTs to make a swap. However, you cannot make a swap to make a CNOT. A swap doesn't entangle. So if you have a 2-qubit state, that's a product. If you do a swap, it's still a product state. Whereas the CNOT entangles qubits. So you can forget about building CNOT from swaps. That won't work. So the trick that will work, and that's a bit of genius from other authors, the idea is to first consider Heis of pi over 2. Which in a fancy notation would be square root of swap. Right? Half the pulse, if you do it twice, it's a swap. So if you stop halfway, it's the square root of the swap. So that's this matrix, with more stuff in the middle, square root of swap. That does entangle. It's much more non-trivial. And now it turns out that you can build a little circuit using 2 times this root swap, not once, but twice. and 1-qubit gates, and that does the trick. So this is, you know, a nice result coming from Loss and DiVincenzo, 1998. So this is when these things were first analyzed. I'll sketch the circuit and then I'll try to actually demonstrate it to you in my emulator in the computer. Let me first sketch it so you've seen it for sure. So if I do the following, here's my 2 qubits. This square root of swap, you know, twice. So over here and somewhere over here. Square root of swap. And then I put in just the right combination of 1-qubit gates, which put a Z here, you put a S here, you put an S dagger, and here you put an H. So we've encountered all these 1-qubit gates. You know, H is this Hadamard, Z is the Pauli Z, S is actually the square root of the Z. So it's a different gate. S dagger is the conjugate thereof, and then there's another Hadamard here. So the claim is that if you, combine this square root of swap with these 1-qubit gates, this whole thing is the same, you know, equal to the CNOT. And now let me. I think it's this way. You know, CNOT is not symmetric. I think it's this way. Yeah. So this is this notation square root of swap. We wrote like this. So you have to turn your head to. But this is my claim, and now to illustrate this, I mean, you can obviously do this. This is 4x4 matrices that you can multiply, right? So you can do it by hand or in Mathematica. But since I'm planning to show you a bit of this quantum circuit emulation later on, like next week, I try to warm up for that in this particular example. So let me try to share my screen. Hope that works, so you can see my code. So we practice this. There we go. I'm in the Zoom. I can share screen. This will stop other screen sharing. Okay. Yes. Yeah. Okay. Works. So you see what I've done. Yeah, there's various, let's say, computer languages designed to, you know, to work as qubits. And the standard these days is that, you know, you work with Python, and then you load some extension thereof that is designed to handle qubits. And there's, you know, some standards by now. Qiskit is a famous one developed by IBM. There's also a thing called Cirq, developed by Google. And I decided for this situation to work with Cirq. So what I did, you know, I made a Jupyter notebook with some Python code where the first thing I did is, you know, I imported Cirq. So I loaded all these qubit manipulation commands that were written for me. I imported NumPy, etc. And this way I can actually work with qubits in my code. So this was all prepared at home. So let me run you through it quickly. The first thing I do, I set up 2 qubits. So that's, you know, circ.linequbit.range. So, you know, I put them on the line, I make it very small, range 2. A bit later in the course, I will make longer chains and work with them. But for now, it's just 2. And then, you know, so the circ has certain gates in the library. For example, if you look a bit down, I call, you know, circ.z and circ.s and circ.h to build my circuit. But it doesn't have this thing, at least not that I'm aware of. So I made it myself. So what I did is I put in a matrix, which is precisely this high gate matrix. The matrix over there, this array is exactly this matrix over here. So I simply typed that in, and then I told Cirq, you know, use this matrix as a 2-qubit gate, because I know it's what my XXX magnet can handle. So I did that. I did a little check that it's unitary. So I took the matrix, I took the conjugate, I made the product, and I checked it's actually the identity operator. So that's good. Then, you know, I checked. I put in this alpha equals pi over 2, and I checked that this what I get is the square root of swap. So that looks like this. The square root of swap is this matrix, and then if I do that twice, I actually get the swap. You see, -1j, 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 -1j. So that's all fine. And then I simply built a circuit, which is exactly the circuit that, you know, DiVincenzo and Loss told me to build. So I built this thing here. but it's maybe nice for you to see how that goes. So I tell circ, make a circuit, and then start putting these gates. So circ.hb, that's this, right? So the qubit down here is called B. This one's called A. So the first thing I do, you always read these things left to right. So I say put an H on the B line. That's here. So that it does. And then I put this highest layer pi/2. So that's my highest gate, which I call a layer in the circuit. And it touches both A and B. And I put the pi/2 as a parameter. So that's here. And then next thing, you can see is the Z on the A, another highest layer, and then these two S's. And then H, I couldn't do S dagger, so I put an S and the Z, which together make an S dagger, and that's it. And this way, I tell them that print circuit, so I get the circuit in this notation over here. And then, at this point, I can say, well, now run the circuit. That's of course why this is a useful thing. The honest way, to let's say mimic the physical operation of a quantum computer is put an input state, run the circuit, do a measurement. That's the only thing we can do in real life, right? But of course so I could have done that, and this way kind of, confirmed that my circuit is indeed a CNOT. But I was a bit lazy, so since this package obviously knows everything, it's just an algebra package, you could also say, well, simply extract for me the unitary matrix that this circuit represents. Right? Again, you cannot do that with a quantum computer, only by doing lots of measurements. But in this emulation, you can do that. So I took this shortcut and I said, well, give me the matrix. So where's that? It's circ.unitary of circuit with 4 digits. Then it gives me the matrix. And you see this way, you immediately see it's indeed this CNOT with the minus J as prefactor. So it confirms exactly that. So you see the CNOT, right? It has the swap on the second qubit, but only if the first qubit is in the right position. Another way to actually check that it's right is to add a CNOT in the end, which I did in the second circuit. So I added a CNOT, and since CNOT squares to 1, this should mean that circuit is identity. Because the first part makes a CNOT, and then I add a CNOT, and the whole thing should complete the identity. So if I ask the unitary for this whole gang, then indeed you see it's -1, -1, -1, -1. So it's indeed the identity. So you see this way my circ emulator confirms this result. It's Python, but then I import this package called circ. Where is it? So the first letter, you see circ, CIRQ. So that's the name of this thing, and it's built and maintained by Google. There's a big website with a manual and stuff, and it's one way to do this. And of course, so if you actually work with real hardware these days, so you have to tell IBM or whoever has the qubits what to do. And typically, you can upload a circ code or maybe a Qiskit code, and then the place handles it from there on. So this is I think these are becoming the standard languages to handle qubits. But again, so it's important working with this. It gives you certain options that an actual computer doesn't have. For example, I could also say, well, here's an input, run the circuit, now give me the final vector. Right? Again, you cannot do that. In an actual quantum computer, that takes lots of measurements. This is a full state tomography thing. But in the simulator, you can do that. So you have to always see if you want to be really honest and do everything as if it's a real quantum computer, or if you do certain shortcuts, where you use it more, you use Mathematica, so to say. But again, I show this just for illustration of this little nice fact, but also because next week I'll be showing you some bigger notebooks where we actually do some quantum computing on spin chains and molecules, etc. So if you're interested, and this is new for you, maybe over the weekend, you can have a glance at this library and see some things. I'll post this. I guess I can post files, right? I'll post this little thing so you can see how it's done, and there will be a few more after the weekend. Okay, so then in my build-up, I skipped the second type of interaction, which is the what Yuan calls XX. So this one here. So you can ask the same question if I pulse my X Should it go away, or Andrea, there's something. If I pulse my x-axis, can I make a CNOT? So it's again an interesting question. It's my second exercise, so I'm not going to give you how it's done, but let me give you the clue. I learned this from a paper by Norbert Schulch and Seward, 2008, so a bit later than the other one. So typically, let me give a few clues. So the second case, which I first skipped, the x-x interaction. So if you look at what is the native operation that you typically get, it turns out you cannot make the swap or the, but what you do get is a thing called I-swap, which is this matrix. So it's 1, 1. And then it's a swap in the sense that you interchange the middle two states, but there's an extra I here. So this is what happens if you pulse this x-x interaction for some time. You can probably see this quite easily. X-x is like a hop of the middle two states, and if you exponentiate that, there's this I, and it doesn't go away on you. So this is I-swap. Now you get to play the same game. Can I use an I-swap and put 1 qubit gate to make a CNOT? Answer is you can't. But what you can do is actually build a circuit a bit like this, where you use 2 times the I-swap, and you use 1 qubit gates. And then you can actually make a CNOT. So it can be done. It's known how to do it, and it's my story in the sense that all 3 interactions are good enough for universality, which is important, right? It means if your quantum computer design is essentially this kind of physics, you're okay. You can do it. You can build everything that's needed. So again, this would be an exercise. I'm not going to do it here. Okay, so I think that's all going very well. Now I'd like to do a little digression, which is a bit away from standard circuits, 1, 2 qubit gates, etc. So I'm going to look at one of these cases and imagine it's not 2 qubit interactions, but more than that, right? So, and I'm going to do the obvious thing for, I guess, a physics audience, which is to build a chain rather than 2 qubits alone. So, and if you wish, it's in a sense like a step towards quantum simulation rather than digital computation, but it's a bit in the middle. So, my next section, which I guess...
Sorry, Kareljan.
Yes?
I have a question.
Just 1 second, I'm coming. I get beautiful XX chain. Question?
No, I have a question, then maybe there are some others. So it would be possible to construct, for instance, the Heisenberg Hamiltonian just by using some Ising Hamiltonian in this scheme?
Well, I guess but the only thing you can do is, if your native gate is Ising interactions, you can make unitaries, which are exponents of this interaction running for some time. And then you can compile whatever you like into those building blocks, so to say. So if you wish, you could compile this Heis alpha, which is, it's a unitary. It's native to the XXX architecture. So if that's my architecture, this is a very cheap gate. Yes. If you really want it, but your architecture is Ising, then you have to compile, so to say, this gate on the Ising basics, which you can do, but it's a bit ugly.
So there is nothing.
So yeah, and so there's lots of there's lots of theory of how you optimize this compiling. So how you minimize the number of 2 qubit gates and things like that. And but I think the present situation of developing quantum computing is that gates make mistakes. It's hard to have many of them, so it's really important to be as efficient as you can. So if you have your system, look what is native, and then try to compile whatever you like to do into the native gates as efficiently as possible. That's the name of the game.
And then another question I have, well, in physics, we know that, okay, spin 1/2 is just a possibility, but you can consider spin 1, spin 3/2, Hamiltonians.
Yeah, so clearly you can imagine indeed spin S or atomic systems with lots of levels. So I guess the name people use is qubits, so where, with dimension d. And indeed, for certain problems, it can help to have dits rather than bits available. I did an analysis recently for a graph clustering quantum algorithm, which we implemented on qubits rather than bits. And we show in that paper that for that purpose, that's a better scheme, it's faster.
Because I think they can shorten the length of the circuits in some cases, maybe.
Yeah, so typically you will get fewer gates, but of course the gates by themselves are richer because they have more dimensions.
Yes.
But yeah, you can imagine, for example, if you have large d qubits, for example, in photonic designs or so, that's an option. Then you can compile your favorite algorithm into those and see how well that behaves. Okay, so my theme for now is not going to dit, but going to lots of qubits that are coupled.
Okay, sorry, if there are questions from the students, sure. I don't know.
Yeah, please.
So if you have a question, please speak on the microphone.
Yeah, so please let me know if there's anything.
Just speak.
Maybe even putting the camera so that we see.
They can just speak on the microphone.
Okay, so continue. Let me know if anything comes up, right?
Yeah.
So the idea is here, so until now we talked about coupling, certain language, two qubits in a certain way, and that way we would, generate a quantum gate. Now it's natural to imagine having qubits coupled, more than two of them together. So, and for physics, the natural thing is, imagine that these XY couplings or these XX couplings, you actually have them on, so to say, in a chain configuration, in a 1D chain. So that gives me H, let me call it XX, my Hamiltonian, a big sum. Let's say X equals 0 to n minus 1. That's for some reason I write it like this. A coupling JX over 2. Now I have X. X couples to X plus 1. And Y couples to Y, X plus 1. And let's imagine, we do open boundary conditions. So the chain has a beginning and an end, and it doesn't loop around. And yeah, so if you see what this as matrices, so every time there's a pair of qubits next to each other, it's a 4x4 interaction, so to say, on that subspace. It looks like 0, 0, JX, JX, 0, 0. Yeah, but again, it's now it's on over this entire chain. Now, there's a number of things we can say about this. First thing, which I think many of you know, this chain can be mapped to free fermions doing a Jordan-Wigner transformation, and then it becomes a problem of fermions hopping on a chain rather than spins flipping on a chain. So there is, the free fermion mapping, which goes as a Jordan-Wigner. I will come to that later. I will, for today, ignore that, but later I will talk about applications where you want to describe fermions, for example, in chemistry, or Hubbard models, or things like that. And then, you need to map fermions to qubits back and forth. So I'll come to that later, but now I'll just mention it, but use it, right? So I'll stick to the spin chain language. But please, realize that this is going to play a role. Now,
could I ask a question about this? It's from the Zoom audience. Hi.
I hear. Yeah, please ask the
Can you
question.
hear me? Yeah, so I'm sorry, I thought you didn't hear me. My bad. No, so over here, you know that the Jordan-Wigner transformation is a very non-local transformation between all of the things. Right now, we were mapping all the spins to qubit space, and now the fermions would be some very non-local object in this qubits that we have mapped already. So is there some different way we map it once we go to free fermions? I mean, then I have lost, in the fermion language, I've lost all locality between the qubits and so on and so forth, right?
That's correct. So if you do the mapping, then, for example, what you do to the qubits in the middle, has a tail of set operators, these parity operators, and I think that's unavoidable. To implement the correct fermionic statistics, you need to somehow do this. So there's alternatives. So Jordan-Wigner is only one scheme. There's also Baravi-Kitaev and a few other options, but something like this has to be done, and it's always going to be non-local in nature. So in 1D it's not so bad. If you try to do 2D Hubbard, say, this is a big problem, because to represent 2D fermions on a 2D qubit register, these phases are a big headache. But
right.
please.
No, the
yeah.
point was, the next part of the question was that usually whenever you're doing any kind of circuits like this, you care about how many operators you have and how much it scales with the system sizes, etc. If I take a moderate circuit and I try to map it to fermions and I want to simulate fermions, does this mapping actually give me some, does it give me an exponential overhead in the number of things, or is it polynomial? Is it something known?
No, so certainly in 1D, the overhead is pretty moderate. But again, in 2D, it's more difficult, because you have to kind of snake these Jordan-Wigner tails over 2D. And that may mean lots of swaps that you have to build into your code, and those are expensive. But we'll come to that, I think, next week.
Okay, thank you.
Okay, so talking about this thing here. So an obvious choice for this Jx, but not the only one for today, is to take them constant. So if I take, Jx equals a constant, and let me call it minus J0 for now, with J0 a positive number, then, this is a solvable thing. For example, if I look at states with one spin up and the rest spin down, that's Hamming weight 1 in the computer language. The one particle states, if you wish, they have energies, Ej equals minus 2 J0 cosine pi over n plus 1 times J, for J equals 1 to n. So somehow I'm talking about n sides, n qubits, n sides, n qubits, let me call them. And I use this n equals small n plus 1. That's to make contact a bit later with funny polynomials. But so it's simply n qubits, and this is the one body energy that you probably know. It's a free, a cosine dispersion looks like this. So it's a one band, and you can, there's no interaction, so you can pile up excitations filling these bands, and that gives you all the energies. So it's completely standard, solvable, free one system with not much going on. But the dispersion is like this. So there's a bunch of points on this cosine curve that give you the one body energies between 2J0 and minus 2J0. Now, if you do it this way, you see, if you imagine pulsing this interaction to do some interesting quantum control, it's going to be very bad, right? Because there will be energies coming from this, crooked cosine curve that are going to sit in the exponential. So they build up phases, and these phases will interfere in very difficult ways that is not going to be very tractable. So using this interaction to do, let's say, controlled, simple quantum information processing is hopeless. Won't work. So we need a better, smarter choice if we want to use an architecture like this here. And that is actually available and has been explored to some extent. So it goes under the name Krawtchouk chain because it features Krawtchouk polynomials. It's not so well known, so let me give it to you today so you've seen this. Yep. Okay, so I make another choice for my j-axis. And what I'm going to do is I pick my j-axis to be minus j over 2, some constant. And then I take square root of x plus 1 times n minus x. Yeah. So my j's are now space dependent. And if you look at it, you know, they're weak on the edges. So if this is my chain, so the first side is x equals to 0. And the last side is x equal to n. That's how I label the sides. You can see this coupling actually truncates. So between 0 and minus 1, there's nothing. And between n and n plus 1, there's also nothing. And then it looks like this. So it's weak on the edges and strong in the middle. And it has this funny root of parabola shape. Now, of course, there's a reason for picking this particular choice, and that is the following. If I now again do my one particle problem, so to say, one spin up and the rest spin down, I compute the energy, I get the following results. Now I get Ek equals J, and then it's K minus N over 2, for K equals 0 all the way to N. And now if I make a picture of my spectrum, so here's energy. It starts at minus Jn over 2. It ends at plus Jn over 2. But now it's linear. So now it's like this. And now you see it's much nicer and better control, because these energies, it's a linear thing. Everything is now equidistant, so the jumps are all the same, equidistant, and equal to, well, the jump, you know, if I go from k to k plus 1, it's simply j. So j sets this energy scale. Right, so all the, you know, if you now imagine all the time factors, so, you know, e to the minus I t times ek, this type of time factor in the solution for the Schrödinger equation, all these energies are commensurate. They're all multiples of j essentially. And this means that you can expect special things, right? Everything is completely resonant, so to say. And in particular, if you now, seeing that energy spacing is j, if you, for example, tune time to pi over j, you're going to have a resonant situation where all these energies essentially are the same, or it's all 1 and I and minus 1 and minus I, and you get very special behavior. So you can really imagine that if you pulse this interaction, so this thing, the K interaction, the Krawtchouk interaction, so if you do e to the minus I t h Krawtchouk, and you take t, let's say, things like pi over j, then these should be very interesting operators. And that's, I guess, back of the envelope expectations.
One question. Here, since you have like
it's the same. It's for both. Yeah. So the question is, these energy levels. Am I talking fermions or spins? And since there's a mapping, it can be both, right? So in the fermion language, this will be the one fermion state, and I can load. It's still a free problem, so I can fill a band with these guys. In the spin problem, it's the states with one overturned spin. 1, 1, and the rest are 0. So it tells you how this single one propagates through the chain.
Yeah, so my question was that since the states are all equidistant, if I just, from externally, if I give in an energy of J,
okay,
I would expect 1 to 2 fermion or 2 to 3 fermion state will be the same energy. How do I address or differentiate between them, or do I not care? Usually, like in other kind of trapped atoms or something, you need some anharmonicity in the level so that you only look at your computational subspace and not higher excitations. So now, if I give some energy, it will excite anything to anything, at least like anything to anything plus 1 or minus 1. So isn't that a problem for me?
Sorry, I missed 80% of what you said. I'm sorry.
Oh, wow.
Sorry.
Okay.
Sorry, can you repeat the question?
Sure. I was trying to say that since the levels are now all equidistant, isn't it a problem since if I go from a 1 fermion to a 2 fermion state or a 2 fermion to a 3 fermion state, I have the same energy. So if I give an energy of J, I have no way of knowing which state to which state it went as long as it's neighbors. So isn't that a control issue?
Yes, so the question is that because this is so special, if I start making many body states, meaning I'm going to fill a number of these one particle states, there'll be lots of degeneracies, right? The many body spectra will be highly degenerate, which can mean that there's going to be complications as a quantum information register. I'll give you an application tomorrow, I think, where we actually avoid this, but you're right, the spectrum is highly special, but at least it is well controlled, and that's what's important.
Okay, thanks.
So yeah, let me, okay.
Kareljan, imagine I want to do a projective measure of that energy. How I'm going to do it?
Of the energy, that's not so easy, right? Then you would have to, well, you would have to measure in the basis of energy eigenstates, which is very different from the basis of you know, the states localized on one side. Actually, yeah, I'm just getting ahead of my story, but there is actually a nice transformation from between those two bases. So if you use that and then measure, you determine the amplitude for being in a certain energy state and project into that basis. Yeah. Okay, but so you know, I gave you the spectrum. Maybe let me give you a few math details just to be sure, without deriving much. So then, at least you know why this thing is called Krawtchouk. So so these one-body eigenstates that I labeled with my k over there, they look like this, obviously. So I can decompose them with some numbers on the what's called the computational basis. So that's, you know, that can always be done. Those phi's them, I put out some factors, some combinatorial factors. So there's an n over x, an n over k binomials, and then a 2 to the n. And then there's a thing called kn, k comma x. And these things are polynomials, and they're known as Krawtchouk polynomials. That's why the chain has this name. So let me be completely explicit. What is the Krawtchouk polynomial n labeled by k and x, so by two integers? It's the sum from I equals 0 to k of minus 1 to the j. So this is a j. And then it has x, j, and then it has n minus x, k minus j. So these things, again, are called Krawtchouk polynomials. So you see the whole thing is extremely solvable, and even know exactly the one-body eigenstates. So this actually, you know, for proving some advanced things about the system, these things are useful. We used quite a bit of it when we did analysis, but I guess for today it's simply, I mentioned this so that you've seen this and know where the name comes from. Okay. Now, to finish, last 5 minutes, a few sort of fun facts about, you know, the time evolution operator for this Krawtchouk chain. So right, so this U over here. So again, imagine that, you know, our experimental friends, sorry?
So I'm wondering, where are the variables of the polynomial?
Whatever you like. So you can view it as a polynomial in X or in K.
Yeah, but here you write it as integers. That's why you write the binomial coefficients, right? I mean, as a polynomial, there should be, there should be any.
Yeah. So I guess the polynomial would be, you multiply this with x to the something, and you sum out. So I guess it's coefficients inside polynomials.
Oh, okay. Yeah. Thanks.
Yeah. Okay. So, but now again to complete today's lecture. So imagine, your experimental friends, they built a Krawtchouk chain in their lab. So they have qubits, and they engineer these couplings just right, the way I want them, with these square roots, etc. And they can play with it. So they can actually pulse this interaction for time, let it act on initial state, read out the final state, and see what they get. Actually, people have tried this quite a bit with varying success. I think the one-body dynamics they have seen for reasonably big systems with 10 sites or so. The many-body dynamics, I think, so far not. But it's an interesting thing to do. So I give you 3 sort of fun facts for this Krawtchouk chain business. The first thing goes under the name PST, and that means perfect state transfer. And it employs exactly what I said before. So just to be sure, this thing, e to the minus I, and then pi over j, and then the Krawtchouk interaction on n qubits. If you play with this, and for example, you take this unitary and you apply it to the initial state 1, 0, 0, 0, 0, 0. What you'll find is that the output state is actually 0, 0, 0, 0, 1. If you apply it to the state 0, 0, you'll find the output state is 0, 0, 0, 0, 1, 0, etc. Where maybe some phases in the way, but this is what the basis transformation looks like. And so in general, if you see what this U does, essentially does a left to right reflection. Sharp, with exact amplitudes equal to that. Which this could never happen for the XY chain with a cosine, because then these energy factors are all over the place and they don't line up nicely. But since here, as I mentioned, after time pi over j, all these phases have lined up to be very similar, they can do this kind of magic. And so in particular, what this means, if you imagine now, you have this, this physical. And at time 0, you take a qubit that you encode in the leftmost spin. So let's say some qubit, some state alpha or so, and everybody else is 0. Then if you wait, and you let the thing time evolve, and you stop the clock at pi over j sharp, then this final state has ended up over here. So initially it's this with everybody 0, finally it's with everybody 0. So you can view this as like a wire. It's a transfer of a state through a wire, right? So if the chain makes a wire, let's say between the left and the right end of your laboratory, you can transfer your favorite qubit state via this dynamics to the other side. And it's perfect. There's no approximation, so it's called perfect state transfer. And this is a beautiful subject, which was quite a bit of literature and research that was done. Second fun fact for Krawtchouk is GHZ generation. So that's another shorthand that's standard in quantum computing business. What is GHZ state? It's the state on n qubits, which is a superposition of everybody in the 0 state plus everybody in the 1 state over root 2. So this would be GHZ. Let's say on n qubits. This is a very funny state. It's highly entangled. It's difficult to make starting from product states because of this very special structure. But actually, the Krawtchouk dynamics gives you a very quick way to get there. So there's a claim that if you start from the state, the 1-qubit state, which is 0 plus 1 over root 2. That's an easy to make 1-qubit state. So you take the 0 state, you put the Hadamard, and you have it. If you do this, let's say to the power n, so you have n qubits, and you put them all in this state. That's your initial state. And then you hit the thing with the u that I just had. So the pulse of the Krawtchouk interaction with time pi over j. Same operator I used for perfect state transfer. Then the claim is that, modulo 1-qubit rotations, this thing is exactly the same as the JHS state. So that's quite remarkable, I think. So you make this crazy state, which is rather difficult to make in other ways, by a single pulse, essentially, of an n-body interaction. And again, it's an exact thing that you can do. So that's the second fun fact. And now the final one, and then I hope I finished just in time. Yeah, so let me put it here. That's a thing which I learned from a paper of Bose, who's one of the experts on this business. So there was the following, that's it's a rainbow state preparation. So again, a funny state that I should explain. What is the rainbow state on n qubits? It's the following. So if this is my, let's say I take n equals 4, it's a state with, the rainbow comes from this little picture. And the picture means that if I put 2 qubits under this kind of arc, I make the Bell state. So that's the 2-body state for these 2 qubits is, let's say, 1, 0, plus 0, 1. Maybe, I guess like with a minus, typically, over root 2. So this is Bell state on 2 qubits. This is the singlet, if you wish, for the spin a half. So the rainbow state would be a state where, there's these Bell states between the first and the last qubit, the second and the one but the last, etc. Right? Meaning this is a state with maximal left-to-right entanglement, as you can see, because all these arcs give you a contribution to that. Again, this is a interesting, funny state, and the claim is that you can actually make this state in a very simple way. Namely, you take the Néel state, which is very boring, classical state, looking like this. No entanglement, nothing like that, a product state. You do an operator, well, I have to be careful, so let me call this U tilde. It's not the same U as there. Yeah, and that gives you the rainbow state. Where this U tilde is, it's not the pulse like this, but U tilde is actually, well, it's built in a certain way, which has a centerpiece e to the minus I t h Krawtchouk. But now for t equals pi over 2j. So I do the same trick I did before today in these lectures. I take a square root of my favorite unitary to make another unitary. So this is like the half pulse for Krawtchouk. I put, there's a bit of complication because I need to sandwich this between two rather simple but non-trivial operators to make the story complete, but that's a bit too much for now. That gives me a thing U tilde, and that U tilde really in one go, one hit, sends Néel to rainbow. And gives a very short way to maximally left-right entangle the chain in an exact way, no approximations. So that's quite remarkable, I think. Actually, it turns out if you build the same operator for the constant coupling chain, you can try. You get a similar thing, but it's not perfect, obviously. So you get a highly entangled state, but it's not perfect, like this one is perfect. So yeah. Final close, just also for documentation. A lot of what I discussed today is very nicely summarized in a PhD thesis. Let me put it here as a reference, so a big reference. A PhD thesis of a student in my group called Groenland. So for his thesis, he studied lots of these things, this Krawtchouk change and protocols to make funny entangled states, etc. And in his thesis, he made a very nice introduction where a lot of this material was that I presented today. I took from that introduction. So I'll put a link on my notes so you can find it. It looks like this as a book. So I think this is a good moment for me to stop, but there may be questions that I can still take at this point.
Yes, Andrea.
Sorry, that dispersion relation is the entire Brillouin zone or half?
I think it's the same Brillouin zone that you would have for the constant couplings.
So there is a discontinuity at the edge of the Brillouin zone, right? Of the dispersion relation. It's an open system.
Yeah. So you see. So the constant coupling thing looks like this, right? And in a sense, what this modulation of the strength does, it kind of straightens the dispersion. That's how I like to understand this. So rather than having the cosine, it has this thing here.
Okay.
And for the rest, it's very similar. It's like a deformed cosine dispersion, but with nicer properties for time evolution.
Okay. So it shouldn't be a continuous function. I mean, it's possible to have a. It's not a periodic function.
No, clearly I have trouble closing the chain, right, with this. So
okay.
it's really for the open system that this can be done.
Okay. No, because you get chiral mode. You don't get. Okay, because it's open. Okay.
Yeah.
You don't get left and right moving, but just a chiral excitation.
Yeah, if you wish, but of course it bounces off the boundaries and goes back and forth.
It doesn't bounce. Okay. Okay.
Okay, if you have question, please ask on your microphone. See.
So I missed the imperfect state transfer. U is e2 minus pi over. I don't see really. It's a particular value of the time.
Sorry, yeah. So it's the J.
Okay.
That's here. This J. That sets the scale, and so the spacings are exactly equal to J. So the magic choice of time is pi over J.
Okay, and also I have a more general question. You mentioned the Jordan-Wegener, so you can understand the spin through the Jordan-Wegener. But if you want to simulate the fermions, I would like to see probably a system in which you don't have a plus or minus, but 0 fermions and 1 fermions, really done with fermions. That would be a model of computation without arriving to fermions with the Jordan-Wegener. So it seems to me natural somehow to study the fermions by doing always Jordan-Wegener from spins. Maybe because it's difficult to do quantum computation with fermions, 0, 1 in several sites.
Yeah, no, I understand. So I think you can do that, right? So you can build the whole formalism on fermion number states rather than spin states or boson states. I think in the end it's equivalent. You also do Majorana fermions. I think in the end everything is mappable, so they're equally strong in terms of what they can do for you. Yeah, I think so. Yeah, certainly in 1D, I think it's all relatively simple mappings, but beyond that, it's non-trivial mappings.
Okay, so if there are no questions from the students, then we can close the session here. Okay, so thank you, everybody.